Welcome back to this. We will continue from the last part on the eigenvalue eigenvector for a simple 2 by 2 matrix. Okay, now we will have some examples to actually work them out in detail, and also probably slightly more involved examples in this session. Okay. So first let us find out the eigenvalue for this famous matrix known as the Pauli spin matrix X component. And so the eigenvalue equation is this matrix multiplied by a column xy is equal to lambda times xy. Okay. Therefore, if you recall that it was a11 minus lambda, so you can immediately write the determinant that goes to 0 as minus lambda 1 minus lambda is equal to 0. Please recall that. You see a11 minus lambda, a12, a21, a22 minus lambda. A11 and A2 are zeros, therefore you have simply minus lambda, and these are 1s. So you have that, which gives you, it is very simple, is lambda square minus 1 is 0, therefore lambda is equal to plus or minus 1, two solutions. Let us look at the eigenvectors. So if it is 0, 1, 1, 0, xy is equal to lambda is 1, and therefore this is xy. Now if you write this as an equation, you see that it is y is equal to x, and here x is equal to y, which is the same equation. But we want x square plus y square to be 1. Therefore, if y is equal to x, then what we have is y square plus y square. So I am using the fact that x is equal to y square plus y square is equal to 1, or y is equal to 1 by root 2. Okay. We will take the positive root for this. Therefore, x is equal to 1 by root 2, y is equal to 1 by root 2. Okay. So the eigenvalue lambda is equal to 1 for this matrix 0, 1, 1, 0. The eigenvector xy is equal to 1 by root 2, 1 by root 2. Now for the eigenvalue lambda is equal to minus 1, you have to solve this equation 0, 1, 1, 0. X prime y prime is equal to minus x prime y prime, and that this equation is nothing but x prime is equal to minus y prime. Okay. The first equation is actually y prime is equal to minus x prime, and the second equation is obviously x prime is equal to minus y prime. But again, x prime square plus y prime square, we will keep that as 1. Therefore, since it is square, you know that it is going to be y prime square plus y prime square is equal to 1, which means y prime is equal to 1 by root 2. Okay. But the solution is, if y prime is 1 by root 2, then the x prime is minus 1 by root 2, because it is minus y prime. Therefore, lambda is equal to minus 1. The solution x prime y prime is 1 by root 2 minus 1 by root 2 and 1 by root 2. Okay. Now this minus plus, this sign is arbitrary, because if I choose y prime square is equal to 1 by 2 and y prime, I can also choose minus 1 by root 2. The overall sign of the eigenvector is not important. Sign of the eigenvector is not important, is not significant. We do not need to worry about that. That is, if you write a11, a12, a21, a22, if you had xy is equal to lambda times xy, then this equation is the same as the other equation a12, a21, a22. Minus x minus y is lambda times minus x minus y. Therefore, it does not matter, but the relative signs between x and y are important, because that is how the eigenvectors are defined. You recall the previous one. In the first eigenvector, the elements are different, 1 by root 2, 1 by root 2. In the second eigenvector, the elements have an opposite sign between them. That is important. But if instead of writing this minus 1 by root 2 plus 1 by root 2, if I write this as plus 1 by root 2, then this must be minus 1 by root 2 in order for this equation to valid. So if I multiply this whole vector by a minus sign, it does not matter, it is irrelevant. So eigenvectors are important, and eigenvectors are defined to within a sign, technically to within a phase factor. A phase factor is e to the I delta, and such things will come in when the eigenvectors are complex, and then the normalization conditions will be slightly different for that. Okay. We will see it in the next example of the polyspin matrix anyway. Okay. So therefore now we have two eigenvectors, namely for this matrix 1 0 0 1, sorry, for this matrix 0 1 1 0, lambda 1 lambda 2, 1 by root 2 1 by root 2, and 1 by root 2 minus 1 by root 2. Now if we want to write this in a very specific form, namely if we want to write this as 0 1 1 0, incorporate both the eigenvectors together. If we write this 1 by root 2 1 by root 2, and then you write this as, sorry, this is minus 1 by root 2, okay, minus 1 by root 2 1 by root 2. If you want to write that, then this equation you can verify by a simple algebra that this is what it is, minus 1 by root 2 1 by root 2 1 by root 2 1 0 0 minus 1. So now you call this as an orthogonal matrix. These are real eigenvalues. Therefore you see that this matrix is also Hermitian. This is a Hermitian matrix or symmetric matrix essentially, because the elements are real. For a symmetric matrix, you see that the symmetric matrix is now A, an orthogonal matrix O is equal to the orthogonal matrix O times the eigenvalue matrix lambda, where the eigenvalues are the eigenvalues along or the matrix elements along the diagonals. Okay. This is a very standard form. If you have to worry about only one eigenvalue, then this is not a matrix, but this is a column vector. We had the two previous equations, A of xy is equal to lambda 1 times xy. So those are two independent equations. This is taking care of both the equations in a single form. But what is important is, if now you multiply by O of t on the left hand side of this matrix, and you have this matrix A and O, then you have O of t on the right hand side also to be multiplied on the left, and O times lambda matrix, and you know this is for an orthogonal matrix, this is the identity matrix 2 by 2 times lambda, and therefore what you see is O of t A O is now the lambda matrix. So what you have done is to take the matrix A 0 1 1 0, which is off diagonal and you have, through the process of this O of t is going to be 1 by root 2 minus 1 by root 2 1 by root 2 1 by root 2. Now you put this matrix in between the two orthogonal matrices 1 by root 2 1 by root 2 minus 1 by root 2 1 by root 2. You see that what you have done is you have got the eigenvalue 0 1 0 0 minus 1. Okay. Therefore you have diagonalized this matrix. Diagonalize this matrix. So you have performed a transformation on the matrix that you were given. The transformation is, this is called a similarity transformation in matrix, when you multiply a matrix with a matrix on the left hand side and its inverse, or its, in this case the orthogonal is the inverse. Therefore the similarity transformation is for any matrix, if you have B, the similarity transformation, if you multiply by A inverse, and this is a C, then B and C are similarity transforms of each other. In the case of orthogonal matrix, what you have is, you have used the orthogonal, the inverse as the O of t. This way, this is A is O of t and A inverse, the inverse of O of t is O, therefore you have done that. So diagonalization is also an immediate consequence if you find all the eigenvectors. If you find all the eigenvectors and you put them as columns in your matrix and you take the inverse of that eigenvectors on the left hand side and you multiply your original matrix, you have actually diagonalized. Therefore, the eigenvalue process is the process of diagonalizing and obtaining what are called the fundamentally characteristic values associated with that matrix. The word eigen means characteristic, and we have found the characteristic values associated with the matrix 0, 1, 1, 0. Now, the eigenvalue matrix is 1, 0, 0, minus 1. Two things are immediately obvious. Determinant of sigma x, this is sigma x if you recall. Determinant of sigma x is minus 1. Determinant of lambda is minus 1. The determinants of the original matrix and the determinants of the eigenvalue matrix, you see, are the same, and the determinant of the eigenvalue matrix is the product of eigenvalues. Therefore, you see that if you take any matrix A, determinant of A is nothing but the product of the eigenvalues of A. Then there is a quantity called the trace. The trace for any matrix, if you have A I j as its all its elements are denoted this way, then the trace of the matrix is the sum of all its diagonal elements sum over I, A I, it is called the trace of the matrix A. So in this case 0, 1, 1, 0, the diagonal elements are 0, therefore the trace of this matrix is 0. The trace of the lambda matrix, which is 1, 0, 0, minus 1, is also 0. Therefore, you can see the trace of A is the sum of its eigenvalues. By the way, I am not proving any of these things. In the first instance, let us worry about what the properties are and how do we make use of them, what do we understand from them, and so on. In the second stage of quantum mechanics and later, you can worry about what are the proofs and other, how do I verify that these things which were told to me are actually true. The proof is, small amount of mathematics, you can definitely do that. But let us understand that the eigenvalues, that is the reason why they are called the characteristic values. That for any given matrix, the property, determinant is a property, is a number associated with the matrix, and that number is nothing but the product of the eigenvalues. So finding out the eigenvalues is also one method. The sum of the diagonal elements is a trace of the matrix, that is the sum of the eigenvalues. So these are all what are called the invariants associated with the matrix. Okay. Now this is for the real problem. Let us do a complex or what is called an imaginary matrix like what we have sigma y. Let us do that. 0 minus I, 0. Now let us find out its eigenvalues. 0 minus I 0 times xy is equal to lambda times xy. Okay. Therefore, lambda is this whole thing is determinant you have to write as minus lambda minus I minus lambda, that is equal to 0, and this is nothing but lambda square. Please remember minus I into minus I, therefore this is minus 1 is equal to 0, lambda is still plus and minus 1, two eigenvalues. Okay. Now therefore, let us find out the first eigenvalue 0 minus I 0 x y is equal to x y, lambda is equal to plus 1. Okay. Then you can see right away that this is minus I times y, the first line is that, is equal to x. What is the second line? Obviously it should be the same as the first line, but just verify it. I times x is equal to y. Okay. If you multiply this by minus I, the second line Ix, you get minus Iy, and of course minus I into I is 1, therefore you get x is equal to minus Iy. So it is the same equation. Okay. It is a linear system, the determinant is 0. Okay. That is how we got the eigenvalues, therefore this is the solution. So if Iy minus Iy is equal to x, essentially y is x by minus I, which I would write it as Ix, because 1 by minus I is plus I. So we have an equation which is y is equal to Ix. If we do y square plus x square to get to the normalization factor, something funny happens. You see, y square plus x square is actually x square minus x square, which is equal to 0. This cannot be normalized the way we have done it. But when complex entities and imaginary entities are involved, the normalization is not done this way. Please remember the Hermitian adjoint matrix. Hermitian adjoints. Please remember the transformation from orthogonal to unitary. You recall when we did the orthogonality, we proved that the rows are orthogonal to the other rows. The rows are orthogonal to each other. The columns are orthogonal to each other. But in a unitary matrix, we were very careful in defining that one row and the complex conjugate of another row are the orthogonal things. I mean, you take the product of those, that is what will become 0. Therefore, here if you write y is equal to Ix, you must take absolute y square plus absolute x square is equal to 1. This is required for complex eigenvectors, and this is the definition, and therefore you will see now if the absolute value of Ix is of course x. So y square plus x square is equal to 1 is nothing other than absolute x square plus absolute x square is equal to 1, or x is equal to 1 by root 2. Okay. And now we can say y is equal to I by root 2. Therefore, the eigenvector xy is 1 by root 2 I by root 2. The second eigenvector is obtained by solving with the eigenvalue lambda is equal to minus 1. So you have 0 minus I 0, x prime y prime, and that is equal to minus x prime y prime. So you have minus I y prime is equal to minus x prime, or I y prime is equal to x prime. The second equation is the same as that. Therefore, y prime is equal to x prime by I, or which is minus I x prime. Again, absolute y prime square plus absolute x prime square is equal to 1 implies that the I disappears, because minus I into plus I, when you take the absolute square, essentially it is the number into its complex conjugate. Therefore, minus Ix into its complex conjugate, which is plus Ix, therefore that becomes 1 x square. So this is equal to 1 implies again x is equal to 1 by root 2, and therefore your eigenvalues x prime, eigenvectors x prime and y prime are now, since we wrote y prime is equal to minus Ix prime, and if we write x prime as 1 by root 2, this will be minus I by root 2. So the second eigenvector has a sign change, except that is also a complex number. Okay, it's an imaginary number. Therefore, what you have is 0 minus I 0 times the first eigenvector is 1 by root 2 I by root 2. The second eigenvector is 1 by root 2 minus I by root 2. So if we put both the eigenvectors together in the same way that we did for the previous problem, then the matrix is that this eigenvector matrix comes first, I by root 2 minus I by root 2, and then you have the eigenvalue matrix 1 0 0 minus 1. Okay. Now another important thing, this is a unitary matrix. This is not an orthogonal matrix. Okay. It's very easy to check that, because the square of the columns or rows, absolute square of the columns or rows will give you a total of 1. And if you take column 1, 1 by root 2 and I by root 2, and if you multiply this with the, in the sense element by element, if you multiply this with the complex conjugate of the column 2, please remember 1 by root 2 does not change, this becomes plus I by root 2, multiply element by element, then what you get is 1 by root 2 into 1 by root 2 plus I by root 2 into I by root 2, and that is minus 1, therefore you see this is 0. So this is a unitary matrix, the columns and rows are orthogonal to each other in the sense of the complex quantities involved. Therefore, this being a unitary matrix, what is its inverse? U inverse. U inverse is U dagger, which is the Hermitian adjoint. So if it is a Hermitian adjoint, this is nothing other than U transpose star. So U is 1 by root 2, I by root 2, 1 by root 2 minus I by root 2. So what is U T star? U transpose is the transpose, so let us take the first column, it becomes the first row I by root 2, but its complex conjugate that you have to take, therefore this is minus I by root 2. And the second column, if you take that, this becomes 1 by root 2 minus I by root 2, but it is a complex conjugate, that therefore this becomes plus. So this is U T star, this is U dagger. Okay. Now you can easily see that if you write U dagger 0 minus I 0, U, if you write that, which is this matrix, is now U dagger, because you have multiplied it on the left with the U dagger, and this is U and times lambda, and the definition of the unitary matrix is that this is equal to identity, therefore this is lambda. So eigenvalues are still real, eigenvectors are now complex. Eigenvalues of a Hermitian matrix will always be real, there is a very easy proof to do that. I will not do it now, maybe I will give it as an assignment or a problem. Therefore eigenvalues of these are all Hermitian matrices, 0 minus I 0 is a Hermitian matrix. Therefore the Hermitian matrix is diagonalized by a unitary matrix. A symmetric matrix is diagonalized by an orthogonal matrix. The connection between these two things is very important, that is why this was mentioned in the previous lecture also. You have to see that. More and more such examples and some other real problems as we go along will reinforce this concept again and again, and I am sure you will get familiar with that. So eigenvalues and eigenvectors are extremely, they are very resourceful. Now what about the eigenvalue for the z component, sigma z, 1 0 minus 1? It is a diagonal matrix already, therefore the lambda is already 1 0 0 minus 1. Therefore what is the unitary matrix which will diagonalize this? Or what is the orthogonal matrix which will diagonalize this? Identity matrix, because this is already diagonal. Therefore you can only write 1 0 0 1 multiplied by 1 0 0 minus 1, its adjoint or whatever it is orthogonal is still the same thing, and that gives you 1 0 0 minus 1, trivial, silly to write this. Okay. Since the matrix is already diagonal, its eigenvalues, eigenvector is just the identity matrix. Okay. It is very important to understand these things in detail. So let me leave this lecture with a few specific problems of the eigenvectors. Okay. Now we will do one more simple problem of a 3 by 3 matrix before we close this lecture. Okay. And that is it is illustrative of slightly more detailed algebra, and very often when we do these lectures you will find out that the simplest things are explained very well and the slightly more difficult things are left to you as problems, and you always wonder, does the teacher really know the more difficult problems and so on. Now yes, we do know, but it is important for you to work this out. A 3 by 3 matrix is a slightly more involved example. So let us take this particular matrix A is equal to 5 0 2 0 1 0 2 0 2. Okay. And let us find out this. Of course, I have picked it up from one of the most famous mathematical physics textbooks, Orfken, the book on mathematical methods for physicists. Of course, you can find innumerable such matrices anyway. Physicists. Okay. Now, let's work this out. So, we have to write 5 0 2 0 1 0 2 0 2 x y z. Now, the eigenvector has 3 entries because it is a 3 by 3 matrix. Therefore, there are three components, and if you want to write this as lambda x y z, okay, and find out lambda. Now, look at this matrix. This is symmetric anyway. Therefore, I already told you that it is easy to prove that symmetric and Hermitian matrices have real eigenvalues. So, our lambda cannot be anything other than real. Let us find out what they are. It is 5 minus lambda 0 2 0 1 minus lambda 0 2 0 2 minus lambda. This determinant should be 0. Okay. So, let me not do this algebra, but I will tell you that after factorization the result turns out to be 1 minus lambda into lambda square minus 7 lambda plus 6 is equal to 0. This is easy for you to verify. Just expand the determinant along a row or a column. You will see a cubic equation, and this cubic equation is factorizable into this. Okay. And quite obviously the solutions are lambda is equal to 1, and lambda square minus 7 lambda plus 6 is basically lambda minus 6 into lambda minus 1 is equal to 0. So, now you have lambda is equal to 1, lambda is equal to 1, lambda is equal to 6. I chose this example for the specific reason that we have two eigenvalues which are identical to each other. This is called a degenerate system. Degenerate eigenvalue system, and the degeneracy here is 2. Degeneracy of the eigenvalue lambda is equal to 1 is 2. Therefore, the eigenvectors will have a little bit of a tricky thing to do. Okay. Let us look at the first non-degenerate eigenvalue, lambda is equal to 6. We have the matrix equation as 5 0 2 0 1 0 2 0 2 times x y z is equal to 6 times x y z. Okay. And the equations are, it's very clear, it's 5x minus 6x, therefore it is minus x plus 2z is equal to 0. Okay. Therefore, x is equal to 2z. Okay. Now, we need only one more equation because this is the determinant of this has to be 0 anyway as a homogeneous equation. So, the next equation you see is 0 times x plus 1 times y plus 0 times z is equal to 6y, or y minus 6y, which is equal to 5y is equal to 0, which gives you y is equal to 0. Okay. And the last equation will tell you 2 minus 2x plus 0y plus 2z minus 6z is equal to 0, which gives you 2x, which gives you 2x minus 4z is equal to 0. That is the same thing as this equation, namely x is equal to 2z. Okay. So, the solution is that x is equal to 2z and y is equal to 0. This is the eigenvector system for eigenvalue lambda is equal to 6. Okay. Therefore, now we have a challenge, namely x square plus y square plus z square. If this is equal to 1, then what we have is essentially x square is 4z square plus z square is equal to 1, which means z is equal to 1 by root 5. Okay. If z is 1 by root 5, then x is 2z, which is 2 by root 5, and then y is already 0. Therefore, the eigenvector that we have x, y, z is 2 by root 5, 0, 1 by root 5. Associated with the eigenvalue lambda is equal to 6. Now, what about the eigenvalue lambda is equal to 1? Remember, this is doubly degenerate. That is, this matrix which I wrote down, namely the matrix 5, 0, 2, 0, 1, 0, 2, 0, 2 has now an eigenvector x prime, y prime, z prime is equal to lambda is equal to 1. Therefore, it is x prime, y prime, z prime. You will see immediately when you expand this to the system of equations, you will see this 5x prime plus 0 y prime, but it is 2z prime is equal to x prime, which gives you 4x prime plus 2z prime is equal to 0. Okay. 5x prime plus 2z prime gives you that is equal to x prime. Yeah, so it is 4x prime plus 2z prime is 0. The next one is again y prime is, this is y prime is equal to y prime. That is all it says. It does not say anything else. And the third equation is 2x prime plus 2z prime is equal to z prime, which gives you 2x prime plus z prime is equal to 0, which is the same as these. These two are identical equations, okay, multiplied by 2. Therefore, we have two equations in which now you have two quantities which are not determined. Between x and z, we have to determine one of them. Of course, we can do that by having the squares of x prime plus the squares of y prime plus the square of z prime is equal to 1. But we do not know what y prime is. The equation is y prime is equal to y prime. So, what are the possible values? Can you take any value? Can you take, this will always be the case when you have degeneracies. If the degeneracy is 2, there will be at least one variable, we will have two choices. We have to make two choices. One choice is y prime is 0. If y prime is 0, that gives you one eigenvector. The other choice is y prime is equal to y prime does not tell you that y prime is 0. Therefore, y prime can be anything. So, the other choice is that. So, how do we choose this? Let us do the first one, namely choose y prime is equal to 0 and see what happens. Then you have 4x prime plus 2z prime is equal to 0, which means x prime is equal to minus 1 by 2 z prime. So, if you write x prime square plus y prime square plus z prime square is equal to 1, then you get again x prime square is 1 by 4 z prime square plus y prime square is 0 plus z prime square is simply z prime square. This is equal to 1, which gives you 5 by 4 z prime square is equal to 1, or z prime is equal to 2 by root 5. Okay. So, if that is the case, then x prime is minus 1 by 2, which is minus 1 by root 5. Therefore, we have one column vector, namely x prime is minus 1 by root 5, y prime is 0, and the last one is 2 by root 5. This is lambda is equal to 1 eigenvector, eigenvalue, and lambda is equal to 6 eigenvalue. We have already chosen that, and we remember that to be 2 by root 5, 0, 1 by root 5. Okay. So where is the third eigenvector? If we choose y prime to be any number, what number should it be? Now comes the property of the eigenvector matrix for the eigenvalues which are real, and we know that for a real eigenvalue system, the transformation matrix or the matrix of the eigenvectors will be orthogonal. So if it is orthogonal, then what it means is the following. So we have one column vector which is given by 2 by root 5. We have another column vector 0 which is given by 1 by root 5. This is the first eigenvector, and the second vector we have is minus 1 by root 5, 0, 2 by root 5. And the third eigenvector also, if you put lambda is equal to 1, the question is only about choosing y prime, the question is not about choosing x prime and z prime. Therefore, you remember x prime and z prime are going to be in that ratio. So no matter what you choose, the x prime is minus 1/2. So if you write this as a, this will be minus 1 by 2a, and this will be some constant c. This has to be an orthogonal matrix. Yeah. Now please remember, this column is orthogonal to this column as well as this column. Now if c is arbitrary, you will see that a into 2 by root 5 and then you have minus a into 1 by root 5 will not give you orthogonality, it will not be 0. A into minus 1 by root 5 and then minus 1/2 a here, take the orthogonality of these two vectors. If you do that, then this gives you minus a by root 5, multiplying this element with this element and multiplying this by this, we will also get minus a by root 5 is 0, which tells you a is 0. Therefore if this is 0 and if this is 0, then you do not have a choice, c has to be 1. Okay. Therefore you see, when you have degenerate eigenvalues, it is important to go one step at a time, calculate the first eigenvector and then find out what are all the variables that you can fix them one at a time and ensure that that eigenvector is orthogonal to the existing, the predetermined, already determined eigenvector. In this case it is a 3 by 3 matrix, therefore we are very easily we are able to say that c has to be 1 and these two have to be 0. Therefore the eigenvector matrix now is 2 by root 5, 0, 1 by root 5, then you have minus 1 by root 5, 0, 2 by root 5 and then you have 0, 1, 0 as the eigenvector. What I did not tell you is that this answer would have been obvious to me and obvious if you knew a little bit more matrix algebra from the structure of the matrix that we were trying to diagonalize. You recall the structure of the matrix is 5, 0, 2, 0, 1, 0, 2, 0, 2. Okay. Now in taking the determinant, you recall that this row and this column which has 1 in the middle is not connected to any other row or any other column. You see that all the other elements of this row are 0, all the other elements of this column are 0. When you see such a matrix, you can write down immediately that to be the eigenvalue itself, one eigenvalue, and given the fact that it is 0 everywhere and 0 everywhere, the eigenvector will also be the non-zero. If this is second, it is second, this is non-zero 1, this will be 0, this will be 0, that will be the eigenvalue. Lambda is equal to 1 and the eigenvector lambda is equal to eigenvector is this one. It's easy to see. Okay. So it is important when you look at the matrix, you should also see matrices given. For example, if I give you a matrix 0, 1, 0, 1, 0, 0, 0, 0, 1, if I give you a matrix like this, same answer is applicable. You see, this has two eigenvalues. You remember this element 1 has 0 everywhere on the row and also 0 everywhere in the column. This is not connected to any other. Therefore remember the structure of the matrix is very, very important. The off diagonal elements tell you which elements are connected to which through the row column vectors. So matrix is not something that you think is arbitrary or a mathematician's invention or whatever. It has real values, which elements are connected to which, and you can see that one is not connected to any other. Therefore this has a standalone eigenvector 0 0 1. Okay, you can easily verify that. And you recall that since this is standalone, with respect to the eigenvectors of the other two, this will not contribute, therefore this will be 0. So you will have 1 by root 2 1 by root 2 as the other eigenvector, and the third eigenvector as 1 by root 2 minus 1 by root 2 0, as you have seen in this case. You see the 0 in the middle, 0 in the middle. That is because this element is not connected to this element or this element through the off diagonal links. You have to go through a row, you have to go through a column to see that structure. So you can see that since it is not connected, you can see that the eigenvector for this is independent of the eigenvector the way it is, and in a similar way if you do this matrix you will see that the eigenvector here is given by these 3, and you can immediately also see that these 3 are the rows, the columns of an orthogonal matrix, and they are orthogonal to each other. Okay. So when degenerate eigenvalues are there, you have to be a little bit more careful, and it is important. We will see degeneracy in quantum mechanics. The hydrogen atom has energy levels for its atomic orbitals which are degenerate, and they are n squared degeneracy as n increases from the principal quantum number value 1 to many, and we have the degeneracies there in other systems. When we have a particle in a 2-dimensional box, we have degeneracies for the energy levels. Therefore matrix representations and matrix algebra associated with some of these Hamiltonians will have this characteristic feature. So this lecture was only to introduce you to some of the more elementary but more important conceptual details. We will continue now, we will stop the matrix description at this point of time, and maybe I will give a supplementary lecture at the end of the course or sometime to add some additional properties and things which have been left out of this description. But the next lecture set, the other sets will continue with respect to matrices. This course will contain only this much. Okay. We will continue with other topics. Until then, thank you very much.